All right. So we left off Friday talking about the E2 mechanism, and we left off talking about the products and Zatev's rule and how, excuse me, the more substituted alkene that's formed in the elimination product is major. And we've talked about product distribution before, talking about how you only see it when you have competing processes. And in this case, you have competitive pathways, right? You can eliminate from this side, or you can eliminate from here, right? So we talked about both SN2 and E2. So today we're going to talk about the SN1 and then the E1, and then we're going to move into working through some examples of these and just looking at different aspects of the reaction. So let me grab the SN1 stuff from up here, and I'll paste it below. Right, so SN1, you can imagine the one, we think we talked about this already, but the one indicates that the reaction is unimolecular. What does that mean? What do you think that means when we say it's unimolecular? When we talked about the SN2 and E2 and said they were bimolecular, what do you think the unimolecular means for SN1?
Does it mean it has one substituent?
No, it's not. It doesn't have anything to do with the substituent per se. It has more to do with the transition state and the rate. So let's talk about that. That's a good observation, because the SN1 is more common for tertiary carbons than secondary carbons. Primary carbons cannot do SN1. All right, let me crop this out. It's kind of messy looking. If I can. All right, so it is more specific for primary carbons. I'm sorry, tertiary carbons, and that's a consequence of the mechanism. So let's just do both of these real quick. So again, with all these substitutions, this is a substitution. You want to find your leaving group, which is generally the most polarized functional group, the bond to the most polarized functional group. And this carbon-carbon bond is polarized towards bromine, right? So this is partially positive, that's partially negative, right? So, and this is my nucleophile, right? And then if you notice for SN1, and the same conditions are going to facilitate the E1. That's why I did them together, the SN2 and E2, because they happen under similar conditions. And then SN1 and E1 happen under similar conditions. So we have methanol, which is a protic solvent. And you have your nucleophile, the methoxide anion, all right? So just without going through the arrows, what do you think happens? Like, what's going to happen in this reaction? If you know it's a substitution, what's being substituted? All right, bromine is my leaving group, and we know it's a good leaving group. We can look at the chart, look at the pK of its conjugate acid, and know that it's a good leaving group. But what's being substituted here?
The nucleophile is substituting leaving group.
The nucleophile is substituting for the leaving group. Excellent. It's going to replace the leaving group. So in the product, this is going to look this way right here, boom, and then OCH3, and then plus Br minus. Right. What about the second reaction? Everything is the same except for the leaving group. Is that right? And this is a tertiary carbon, and this is a secondary carbon. But they can both undergo SN1 because of the mechanism, which we're going to talk about in a second. All right. Do you think something new and exciting is going to happen here?
No.
No. You're going to get the exact same outcome. It's a substitution. And so you're going to lose your leaving group. All right. Any substitution is going to have the same outcome. You're going to replace your leaving group with your incoming nucleophile. All right. Any questions about that part? Right. The solvent, remember, SN2 and E2 both require an aprotic solvent due to the nature of the reaction, right? We said that if we did either one of those in a protic solvent, either if it was a nucleophile, it was just going to get solvated and the energy would drop and it would slow the reaction down. And then if it was a base, as in the case of E2, the protic solvent would just do proton transfer with the base and you wouldn't have any elimination or very little elimination. But in this case, it's different. So let's go through the mechanism and then we're going to talk about the transition state, the rate determining step, all of that stuff. All right, so let's take that top example. So we're going to start with this. Right, so the first step in an SN1 mechanism and an E1, I'm just prepping you for that. The first step is the rate determining step. And this is the loss of leaving group. All right, we lose the leaving group. So that's my rate determining step. And I just show it like so. So now this becomes a carbocation intermediate. Let me clean that up some. Right. This is a common intermediate for SN1 and E1. All right, somebody tell me why tertiary carbons are more suitable for this.
Is it because the charge on the carbocation intermediate can do resonance?
Well, no, it's not resonance in this case. If it was resonance, there'd be an electron donor somewhere that could stabilize it. But you're in the ballpark because you're thinking about the stability of the carbocation. Am I right about that?
Yeah.
But it's not stabilized by resonance. Remember, this is a tertiary carbon. So you have this, and let me show you this in a little bit more, or with a little bit more precision. So you have an empty, basically empty p orbital where that plus charge is, right? And so all of those carbon-carbon bonds that are attached to that central carbon are donating electron density towards that, right? We talked about this before, right? This is, and so what do we call that when those dipoles are favoring one dot? How do I put this? Are directed towards that plus charge. What do we call that? We just talked about this Friday too, when we talked about the sp2 carbons in the alkene and how more substituted alkenes are more stable. What was the term we used?
Was it hyperconjugation?
Hyperconjugation. So that tertiary carbon is more stable. Remember the trend. Tertiary is more stable than secondary, more stable than primary, which is more stable than methyl. This is for carbocation. Right, so tertiary is going to be your most stable. And then sprinkled in between tertiary and secondary, you'll have like allylic carbocations that can do resonance and things like that. But yeah, so that the tertiary is the best suited because that carbocation that you make is the most stable. So this is this plus Br minus, right? What do you think about, so with this being the rate determining step, what are two things that can increase the rate immediately? What are two ways that you can increase the rate immediately if the loss of the leaving group is the slow step? Think about just look at the screen and think about what's right in front of you. All right, what could I do to the leaving group? Not this one, but just in general, as if I had to pick a leaving group, do you think if I picked a bad leaving group, that would increase the rate or slow it down?
Slow it down.
It will slow it down. So we know that the rate is enhanced by better leaving groups. Better the leaving group, the faster the rate. What else? When the leaving group leaves and I form this intermediate, all right, what can I say about the intermediate? Do you want it to be less stable or more stable? More stable. So we could say that. So more stabilized intermediates also increase the rate or enhance the rate. Right, those two things right off the break, we can see it's a tertiary carbon, so that's going to be good because you're going to get a tertiary carbocation intermediate. You have an excellent leaving group, so that's also good. So that's going to enhance the rate. So the first step is loss of leaving group, followed by nucleophilic attack. So we're just going to put the nucleophile over here. I'll make it a different color. And normally when you see these nucleophiles like this, even though it's written as an anion and it is an anion, it's never just by itself, right? There's always some counter ion, some cation to keep it neutral, right? So you got, let's just say for the sake of the example that we use sodium methoxide. So Na plus, right? So then once the nucleophile attacks, let me make some room here. Once your nucleophile attacks here, boom, right? You're going to end up with the substitution product. Here. Sorry about that. And then NaBr. And this is a salt. So this is positive and this is negative. All right. But the substitution product itself is what we care about. We don't care about the side products. All right. So it's this plus that. All right. So with the rate determining step, only depending on the substrate, that's why it's unimolecular, right? The rate determining step does not involve the nucleophile. So when we write the rate law, it's only going to be a function of the actual substrate. So K times the concentration of the substrate. Nucleophile doesn't matter. You can have a horrible nucleophile. That does not change the rate. You can dump in gallons of the nucleophile. That's not going to change the rate. The rate is going to be controlled by how fast the leaving group departs and how stable the carbocation intermediate is. All right. Any questions so far? All right. So you have this is the basic mechanism for the SN1. You lose your leaving group, and then that's followed up by nucleophilic attack. The solvent matters. Let me just make another page. All right, the solvent matters because the solvent helps to stabilize the transition state. So in this case, and it also helps to stabilize the leaving group once it leaves. But in this case, so for SN1, it's going to stabilize the transition state and the leaving group after it departs. So what do you think the transition state looks like for this reaction? Right, and let me show you the rate equation, not the rate, but the energy diagram. So we're going to start here. We have carbocation intermediate, and then so this is my start material. That's my intermediate. That's my product, and this is energy on the y-axis. What's on the x-axis? Time. Right. So you start material to intermediate, and the intermediate to product. So the in contrast with the SN2, is the SN1 concerted or stepwise? Based on what we've seen.
Stepwise.
It's stepwise. It's a stepwise mechanism, right? If it's stepwise, that means it involves an intermediate. Right, it's a stepwise mechanism. So when we think about the transition state and the first step being rate determining, and all I care about is, not all I care about, but the only thing that controls the rate is the loss of the leaving group. The transition state is going to look something like this, right? Where we have here, we have a partially broken bond here between the tertiary carbon and the leaving group. So this is bromine. This is partially negative. This is partially positive. And that's the transition, what the transition state looks like, right? So the way that the solvent helps, let me move this down some. What do you think? How do you think the solvent can help there, right there? Keep in mind, bromine is 3 lone pairs, and your solvent, if it's protic, how do you think the solvent helps here? Right, the same thing that it did to the nucleophile in the SN2, which was bad because the nucleophile was necessary to, for the reaction to happen. In this case, the solvent can come in and actually solvate your leaving group, which is good. If you lower the energy of the transition state, you increase the rate. I don't like that color. This will be my protic solvent. Right, so protic solvents they solvate the leaving group. And by solvating the leaving group, they lower, I'm gonna show you on the energy diagram too. by solvating the leaving group, they lower its energy. All right. So that's why when you do the SN, hold up. Right, when you do the SN1, this will be the right. So the transition state would actually be here, lower in energy. So that transition state energy is lower. That's good. That speeds the reaction up. So we see the same. So product solvents do the same thing, but they have an opposite result with the SN1. And SN2, they will solvate the nucleophile, lower its energy, and make it less reactive, which was bad. But the fact that this is unimolecular, when those solvent molecules surround that leaving group, they make it more apt to leave and make it even more stable.
I have a question.
Go ahead.
Can you re-explain why solvating the leaving group in SN2 reactions is a bad thing?
Oh yeah, let me just go back to that page. So with the SN2, remember we said that the leaving group, where is it? Here. We said that the leaving group was a part of the rate law, right? So the not the leaving group, but the nucleophile was a part of the rate law. So it's K times the concentration of the substrate times the concentration of the nucleophile. But if your nucleophile is solvated like this, where the solvent molecules cage it in and surround it, the energy of the nucleophile, you see where I have it in red, the energy of the nucleophile is going to go down. When that happens, that's going to make the activation energy go up.
Oh.
Right?
Oh.
If you decrease the activation energy, the reaction speeds up. If you increase the activation energy, the reaction slows down.
Okay.
Right? And so when we go back to here, you see the opposite effect. When you solvate that leaving group, you're actually decreasing the activation energy. Right? Because remember, this is the activation energy right here, going from start materials to the highest point on the diagram. That's your activation energy. All right. Did that explain it?
Yes. Thank you.
All right. Other questions? Don't let me do all the talking. I know it's President's Day, but we won't get that. So we got to keep trucking. We'll have a day off on Obama's birthday. Let's do that. I don't even know when that is though. All right. So with the SN1, again, solvent matters, the structure of the substrate matters, the leaving group matters. All right. We have the second step, which is the nucleophilic attack, which has no bearing on the rate whatsoever. It does not change the rate. I don't care how good that nucleophile is, it's not going to make that rate any faster. All right. Any questions about anything? All right. So I talked about the substrate itself being tertiary. Other substrates like allylic substrates and benzylic substrates also work. So let me show you that. And then we're going to do E1, which is going to be very, very similar to SN1. So this will be what we call a benzylic, because it's adjacent to a benzene ring. And then we already seen allylic substrates, right? So both of those work is just as good as, well, not just as good, but they both have a stable carbocation intermediate, and so they'll be, you know, they'll be facile for this reaction, in addition to using tertiary or secondary. But primary, you cannot do SN1 on a primary carbon, because that's like one of the worst carbocations that you can make. So the mechanism will probably switch over. All right. Any questions about anything that we've talked about so far?
I have a question. It's
Go ahead.
about the rate law for E2.
For E2?
Yeah.
Yeah, go ahead.
So, okay. So the base is included in the rate law because it affects the overall, right?
Yes, because it's a concerted reaction, right?
Okay.
The base is pulling off the alpha proton at the same time that the leaving is, that's what's forcing the leaving group to leave. So it all happens simultaneously.
Okay.
So that's why and E2 means it's bimolecular. So it's the base and the substrate participating in that transition state.
Okay.
I think I have it drawn right here. So how in the transition state, the base has a partially formed bond between itself and the alpha proton, and then alpha proton leaving, those electrons are going to make the pi bond, and then the pi bond forming is what's forcing the bromine or the leaving group to leave.
Okay.
So all of those things are happening. It's all concerted, and that's why the rate is a two-term rate law, where you have both the base and the substrate participating in that. So good bases speed that reaction up, bad bases slow it down. Good leaving groups speed it up, bad leaving groups slow it down. More substituted substrates, where you can get really highly substituted alkenes in the product, speed it up. The less substituted the substrate is, the less stable your products are. So you get all of those things affect the rate.
Okay. Thank you.
Yeah, good question. All right, let's look at the E1 mechanism real quick, and then we're gonna start doing some examples. Because I know this is a lot of information, but it's also kind of encapsulated in the videos that I sent. So I'm just trying to reinforce it here, and then we're gonna do some examples. Let me find E1. All right, we go. I'm just gonna cut this and put it on a different page. All right. Let me add a page. Sorry about that. So one of the main differences you're going to notice with the E1 when you compare it to the E2 is that you don't need a base, right? The E1 follows the same path as the SN1, right? It's so tertiary, secondary carbons, protic solvent. So that's a big difference between E1 and E2. Favors tertiary, just like the SN1, because you get a carbocation intermediate, and it follows the same pathway as the SN1 all the way up to the intermediate, which at that point, that's where it either eliminates or substitutes. And to be honest, when you have a substrate that can do E1 elimination, it can do you normally see a little bit of both, like a competition between some substitution and some elimination. So the E1, one of the main features is that it does not require a base, at least not an external base. Right, and this is a classic, this is a classic example right here. This is, if you notice, we're using sulfuric acid to do an elimination. So this is a classic example. This is a acid catalyzed dehydration. What does dehydration mean? Anybody?
Removing water.
Yeah, you're losing water. So your leaving group in this case is going to be water. So let me show you the product first, and then we're going to go through how it happens. We can talk about the rate law, the transition state, and all that good stuff. And anything in between. We're going to talk about that. But really, the same factors that facilitate SN1 are going to be the same factors that facilitate the E1. So I'm going to put this here, and then plus water, and then plus H2SO4. Right. So let me say this real quick before we get started. So the sulfuric acid is kind of like a catalyst. So it always gets regenerated. Right. So you'll see that in the mechanism. All right. So this is it's E1. So the rate law is going to be the same as SN1. Rate is going to be K, not uppercase K, K, come on, Russell, times the concentration of the substrate. All right, just like SN1, because it's the 1 in E1 means it's also unimolecular, but it's instead of substitution, it's elimination. All right. So let's talk about that. Let's look at how that happens. So with the E1, what do you think the first thing that's gonna happen here? If I have OH, and we know that that's the leaving group, is OH a good leaving group or a bad leaving group?
Bad.
Terrible. So normally in an E1, unless you have a really, really, really excellent leaving group, first step in that mechanism is going to be to do proton transfer. If hydroxyl is the leaving group, we got to make it into a better leaving group, right? Because OH is a bad leaving group by itself. So we're going to start here, not there. Put some electrons in here. Sorry about that. Let me turn this volume down. All right, so it's here. And then this is, since it's E1, and I neglected to mention this with the SN1, but all the steps are reversible. They're all in equilibrium. So let me make sure we didn't put the error I did. Let me fix these arrows up here too. And you can fix these in your notes. Just show them as equilibrium arrows. All right. So the first thing I'm going to do, and I'm going to make my acid a different color. I'll regret this later because I got to keep changing it. But I'm going to show the sulfuric acid. This is the structure of it. Right. And so the first step is proton transfer. This is not the rate determining step. Rate determining step for E1 is the same as SN1, loss of leaving group. So this is going to come here and do proton transfer, which are acid, which is also acting as a catalyst. You only need really like a drop of acid in order for this to be facilitated. All right. So that happens. And then I end up with what?
Water.
So water as my leaving group. So that, now this is positive. right? Now it's more apt to leave. And I also, I'm gonna put this in brackets. I also have all right, so this is now positive. That's my carbocation. And then I also lose water. So it's plus, let's see if I can copy that. Paste it. Plus that. All right, everybody good so far? So this is the rate determining step right here. Loss of leaving group, just like in the SN1. What I also have is this. Copy. I have the conjugate base of my sulfuric acid. Right, because once I did that proton transfer, now this is the conjugate base. Right? Anybody not see that? Once I pull that proton off of sulfuric acid, I get the conjugate base of it. All right. So now this is the elimination step. This is where it happens on this intermediate, on this carbocation intermediate. So the thing is, right, with the carbocation intermediate, where are my alpha positions? Right, this is the carbocation itself right here. So there is one proton there, but there's nothing I can do with it. So where are the alpha positions here?
To the left and the right.
The left and the right. And they're all equivalent. So I'm gonna make them all the same color. So you got two protons over here. That geometry is terrible. You got two protons over here. So I can fix that. Right? They're all equivalent, so it doesn't matter which one I pull off. Now, it does matter if this ring was substituted, it would matter, but since it's not, it doesn't matter. All right. So the question becomes now, which one of these two entities, either the conjugate base or water, is the base to do proton transfer? Right? Because either one of them can do proton transfer. So let's put that in here. I think I'll prefer to use the conjugate base because it eliminates a step at the end. All right, because if you use water, you're gonna get H3O plus, and then you're gonna have to show the proton transfer between that and the conjugate base. So it's more simplified just to use the conjugate base. So let's just do this and this. Right, so that's gonna give us, man, I mean, I gotta shrink that. That's gonna give us the elimination product. And it's gonna give us our acid back. So it's gonna give us this. Remember, the elimination product is wrong side. The elimination product always ends up with a pi bond as one of the main functional groups that's formed. Right, that's the goal of the reaction, to make that pi bond. So I'll put a pi bond there and also regenerate my acid. I'm just going to write it out.
When you're done.
Plus H2 plus O4. Get that back. Plus water. Right? Water ended up as my leaving group. So it's there. All right. So this is the rate determining step here, loss of leaving group. That's why the rate is only dependent on the substrate. Proton transfer does not affect the rate. The elimination step does not affect the rate. The loss of leaving group is my rate determining step. All right. So for this particular elimination, how many steps are in that, or total are in that mechanism?
Three.
So proton transfer, loss of leaving group, and then this is the elimination step. Let me label that. 3. I agree with you. So what if you had to draw an energy diagram for this particular reaction? How would it look?
Do you want me to draw it? Or?
Right. The first step, the proton transfer step is rapid. So that's going to be just a quick step, exothermic. Right. Really, because you're making a OH bond and you're breaking an OH bond. So that's going to be a really fast step. All right. What about the second step? If that's rate determining, what does that mean for the activation energy? Higher or low?
Higher.
Higher. It's higher than the rest of the steps. So we'll do that. And then, didn't mean that. And then the final step, the elimination, is also going to be rapid. So I'll just draw it that way. This is approximate. Now that's not, I don't know. We don't have the calculations to actually give the values for the activation energy and things like that, because all that stuff has to be calculated. We can calculate delta H, which will tell us, so I'm going to label these as proton transfer, and then this is loss of leaving group, and then this is the elimination step. All right, so proton transfer, loss of leaving group, and elimination. And again, the axis is time, y-axis is energy. Right, stepwise or concerted? The elimination part.
Stepwise.
It's stepwise, right? You go from losing your leaving group to a carbocation intermediate, and then from the carbocation intermediate to the elimination product. So it's stepwise. All right. So what we're going to do, since we only got 2 minutes left, I'm going to stop here. When we come back on Wednesday, God willing, we'll go through and start working through these examples. A lot of them are pretty self-explanatory, but I'm also going to send you a couple of videos today about ranking nucleophiles and about solvent effects to kind of reinforce what we talked about already. So when we come on Wednesday, we're going to work through some of these examples. And then on Friday, I probably will group y'all up and let y'all work through a couple of examples and come back and discuss them. Go ahead, Tia.
It's about the problem we just did.
Okay, go ahead.
So for the elimination step, since you have two, so you have the alpha carbons, but you technically have but my question is, would you have two products since you can do either side?
Okay, good question. No, since that intermediate is symmetrical, like it's the same on both sides, you could just pick a side.
Okay.
There's no bias for one side or the other. Now, if one of those alpha carbons was substituted with a methyl group, then yes, that product would predominate because it still follows Zaitsel's rule. But since it's like it is unsubstituted and symmetrical, it doesn't matter which side you pick. I just picked that side because it will be easier to put the arrows in over there.
Okay. Thank
All right. Yeah, great question. Other questions? Any other questions? All right. So we're going to stop here. We'll pick up on Wednesday, God willing. I'll see you back here, and we'll just keep trucking. And once we finish up substitution and elimination, we're going to move on to conjugation, talking about conjugated pi systems, and then we'll take our next exam. I'm not sure if that's gonna fall before or after spring break. Because I think in spring break, the second week in March. Start on the 8th or the 7th, something like that.
It starts on the 7th.
7 on that Monday. All right. We'll figure out about the third test. We might just wait till after spring break and take it. I hate doing that, but it won't be the day you come back. It'll be maybe a couple of days or maybe a week after you come back. That's fine. We'll figure it out. It's kind of throwing a monkey wrench in the plans because the last time in the spring we didn't have a spring break. So, but we'll get it together. Y'all have a great day. Thanks for your participation, and we'll see you back on Wednesday, God willing.
Thank you. Have a good
All
day.
right. All right, y'all take care.